Welcome to our chemistry course. In this course, we're going to be going through the topics that are typically associated with General Chemistry 1 in college. We're not doing all topics, but we are hitting the ones that are more challenging for students. We're going to begin by looking at the electronic structure of the atom. So we'll examine the atom, what's in an atom, the protons, neutrons, and electrons, and then really focus on the electrons. As we continue through the course, we'll then look at the electronic structure of molecules, and then we will get into the stoichiometry and the energy aspects of the chemical reactions that take place. So we're going to begin here with the atomic structure in this unit. And our learning objective number 1, we're going to learn the properties of and the location of the subatomic particles and how information of each of these can be obtained from the isotopic symbol. So let us imagine for a minute that this blue sphere we have here is the atom. It's a very rudimentary model of it, but there's our atom. What we would have for this atom is we would have in the nucleus the protons and the neutrons. They are in the center, in the nucleus of the atom. This is a very, very dense central core. And 99.999999999 something like that percent empty space. There might be a couple more nines in there. I lost track, but you get the idea. Mostly there's empty space because that core takes up such a small amount of it. So the electrons are able to move about in the rest of the space that is occupied by the atom. Now, I want you to get a perspective of this for just a moment. Imagine a large sporting arena that seats 50 to 100,000 people. And this is a huge arena, and that arena represents the size of the atom. Now imagine a glass marble suspended above the field in the center of the field of the sports arena. That marble would be the size of the nucleus. So the electrons have the rest of that space to move about in, and there's never a crowding issue for those electrons. So here's some information about the electrons, just to give you a perspective. Some of this you need to commit to memory, and some of it is just to give you an idea of the size magnitude. Now, protons and neutrons and electrons relative charge is listed right here. In the relative charge, we've got the protons and the electrons just being an opposite charge, and the neutrons have no charge at all. So whatever charge a proton has, the electron is opposite. Now, there is a measure of charge called the coulomb, and so I've got listed here what the charge is in coulombs, and as you see, as you carry it out to several decimal places, they are identical. Okay, if we go over here to the right-hand side, we see that protons and neutrons have about the same mass. They are not the same, but they are close. So here's the mass in grams. And as we look at that, they are the same to 2 places after the decimal point of the way we've written it here. But beyond that, they do change a bit. Now, the electron, on the other hand, is about 2,000 times smaller in mass than the proton or the neutron. So very, very tiny comparatively. All right, I've mentioned that already. Same charge, but opposite in sign. And let's mention this one last column here, and that's the AMU. You'll learn more about the atomic mass unit later, but since it's mentioned here, this is the scale that we use to measure very small items on the atomic scale. So this is how it's defined. You would take one atom of carbon, and this one atom of carbon will contain 6 protons and 6 neutrons, and you divide it up into 12 equal pieces. One of those pieces would be 1 AMU. So that's the definition of an AMU. So you see that about 1 is the mass of a proton, about 1 is the mass of a neutron, and then your electron is way less than that. Now, memorize these numbers? No, just know the relative charge, but you need to see the magnitude of these values. Okay, so when you want to define an element, we know the periodic table is made up of all sorts of elements. It's the atomic number that defines the element. And the atomic number is abbreviated with a Z, and sometimes it's called the nuclear charge. Now, does that make sense to be called the nuclear charge? Well, what's in the nucleus? Number of that contribute to a charge, it's the number of protons. So yes, it does make sense for us. So that number of protons defines what element you're looking at, okay? When you look at a periodic table, you'll see numbers going from 1, 2, 3, 4, 5 as you work your way across the periodic table. The other number that's important for us is called the mass number. Now, I don't know why they chose A for mass number, but they did. That's the symbol for mass number. Seems like it ought to apply to atomic number, but it doesn't. And the mass number is not a mass, it's a number. It's the number of things in the atom that really contribute significantly to the mass. What would that be? That would be the neutrons and the protons added together. This number does not come off a periodic table. If you look at a periodic table, there is something on that periodic table called atomic mass. And atomic mass is similar in size as a mass number, but it's something very different, okay? So don't confuse it from that number that's on the periodic table. Mass number is the number of protons and the neutrons. So if you're given Z, the atomic number, which is the number of protons, and you're given A, the mass number, which is the number of protons and neutrons, how would you determine the number of neutrons in that atom? Well, A minus Z would give you the number of neutrons. Okay. So we're going to look at some questions here and see if we can utilize this information. On the periodic table, let us look and see what the atomic number of chlorine is. So let's go to my periodic table here and find chlorine on the periodic table. There it is. And which of those two numbers is the atomic number? Well, that's the top one. Okay, so we can go back to maybe the chlorine, and we got our number. Now, what information does that give us? How many protons is chlorine going to have if the atomic number is 17? Well, that means it's going to have 17 protons. All right, let's go to the next question. Now, let us assume, now we're still dealing with chlorine. We know it's chlorine, and we know that it has 17 protons. If the mass number of this atom of chlorine is 37, the question is how many neutrons? Pause, answer, and then we'll see if you're right. Did you say 20? Then you are correct. We would take the 37 minus the 17 to give the number of neutrons. Okay? Now, if we have an atom of chlorine, an atom has no charge. So if in the nucleus it has 17 protons, and we know it has 20 neutrons, how would we determine how many electrons it has? Well, it has to have the same number of negatively charged electrons as it has protons. That's the only way you could make it neutral. Okay, let's look at a periodic table and let's decide what element has an atomic number of 12. So you look on the periodic table, you're looking for the number 12, and the number of 12 is located right there. So what is that element? Certainly easy enough to determine. The element will be magnesium. So now we're ready to define isotopes. Isotopes are atoms that have the same atomic number but different mass number. Now there's lots of ways you could say this statement. You have to think about it because you might see it defined a lot of different ways and you might think they're wrong. But what does it mean if they have the same atomic number? That means they have the same number of protons. Okay, so you could say isotopes are atoms that have the same number of protons but different mass number. Well, what does it mean if they have different mass numbers? What's causing the net mass number to be different? You could say isotopes are atoms that have the same number of protons but different number of neutrons, because that would give it a different mass number. If you have two atoms, they got the same number of protons, a different number of neutrons, that would be isotopes. So different ways it can be defined, but it means the same thing depending on how you say it. Now most elements have two or more isotopes, not all of them, but most do. And you have to use a symbol to distinguish between them. Now when you look at a periodic table, it does not tell you the isotopes. It doesn't tell you the mass number, as I've said before. It tells you a averaging of all the different isotopes. So you can't look at a periodic table and get this information, but if you were given a symbol that looked like this, you would be given the isotopic symbol. So you have got the element symbol, that's what the X represents. At the bottom left would be the atomic number, so that's correlated with the number that you do see on the periodic table. So sometimes you won't see that. Sometimes that'll be not there because it's redundant. It has to be that number. And the top number is really what defines that isotope, is the mass number. So here is an example up in the top left-hand corner, boron 11, and that's how you would say it, and sometimes you see it written, boron-11. So that's what you say when you see something like that. And you should stop and you should determine the number of protons, neutrons, and electrons in an atom of boron 11. Okay, did you say 5 protons? That comes from this number. Did you say 6 neutrons? 6 neutrons is 11 minus 5. And the number of electrons has to be same as the number of protons, so that's why that's the right answer. I already told you that that 5 is not necessary because there's no other number it could have there. That is it. And if you've got a periodic table, you can easily know that the number is 5. But if it's handed to you and you don't have to look at the periodic table, that's kind of convenient. Okay, hydrogen is going to be the only element in which there's different names. Each isotope has their own name. Now we could call the first one we see here hydrogen 1, and when we look at it, it has 1 proton, and thus the 1. Okay, so the proton is the red. This one has 1 proton. This one has 1 proton. This one has no neutrons. A lot of people would look at that and say, oh, it has 1 neutron also. But obviously the picture doesn't show that. The number up there is the number of protons plus neutrons, and there are no neutrons, so it's 1 plus 0, and it gives you a mass number of 1. Now, what are these names? I probably need to erase that, get it out of the way. The names of these isotopes are H1, that's the one we would call hydrogen. H2 is deuterium, and H3 is tritium. Now, the reason that they get their own distinct name is because they are the most distinct from each other as any isotopes. Isotopes generally have all the same, very similar properties. Their chemical properties are the same. The fact that these have completely, by putting in 1 more neutron, you suddenly doubled the mass of the atom. Putting in 2, you've tripled the mass of the atom. It gives it characteristically different, some very different properties. We won't go into all of that, but it does. Okay, so now we need to focus in on the electrons. If you lose electrons or gain electrons to an atom, you will create an ion. Notice I don't say that you would add or remove protons because you can't get into that nucleus and with a chemical process touch those protons or neutrons. So an ion is always formed by electrons either are being lost or gained. So the definition of an ion would be a charged species. So it has a charge, and it's formed by taking a neutral atom or molecules and either gaining or losing electrons. So it's important that we note the electrons. Now the word cation is associated with things with a positive charge. Now a T kind of looks like a plus sign. So there you go. You can keep that straight. Cations are positively charged ions. They are formed by losing electrons. Now this is what throws some students off. They see that plus sign and they want to add because plus always means add. But that's the charge. So we are not adding, we are losing those negatively charged electrons. And that turns it into a cation. So the anion is the negatively charged ion, And how does it become negatively charged? Well, you would add electrons. So electrons that are negatively charged are put in, and it makes it overall a negative charge. So you should be able to fill in this grid with all your answers. We're going to work on a little bit together, and then I'll see how you're doing with a little question that I'll bring up. But let's start with the magnesium one at the top. Now earlier we learned that magnesium had 12 protons. Now if you don't have a periodic table handy, you'll need to get one, because I wasn't very nice and I did not put that number down there below. So we're going to have to look at a periodic table. So we've got 12 protons, and we see no charge written right here. So that means the number of electrons has to be the same. And then we'll take that mass number of 24, we'll subtract the number of protons, and we will have 12 neutrons. Now let's do one that has a positive charge. Let's look at a periodic table, find sodium, and see that sodium has an atomic number of 11. So that means it has 11 protons. Now it's got a positive charge. If it's got a positive charge, that means it's got to have more protons than electrons. So it's going to have 10 electrons, one less electron, and that would give you an overall charge of 1 proton. And then we go to neutrons. We'll take the 23, which is the mass number. We will subtract the number of protons, and we will be left with 12. So here again, we have 12 neutrons. So isotopes aren't things that have the same number of neutrons. These are not isotopes of each other, are they? They have to have the same number of protons first, and then different number of neutrons. Okay, let's do chlorine. Chlorine has a atomic number, we did that one earlier, of 17, and we see no charge written here, so it's going to have 17 electrons, and then we're going to take 35, which is the mass number, minus 17, the number of protons, and we will be left with the number of neutrons. There are 18. Okay, so let's have you work on the next one, and when you've got an answer for it, let's have you choose the right answer. Pause it, choose the answer. Okay, did you pick 18 electrons and 18 neutrons? Well, the neutrons certainly didn't change, because in the previous one we still had same 35. But the number of electrons is one more than the number of protons because of that negative charge. We have to have one extra electron. Okay, so the periodic table is going to be arranged in such a way that the electronic structure will be determined, where those electrons are, and we're going to be heading that into our next learning objective. But for right now, let's just define some things on our periodic table. The first thing that we need to understand is that when you go this way on a periodic table, they are called groups. Now, one of the older names for it was families, and I might slip up and call them families, but more acceptable term now is a group. Groups have similar chemical and physical properties. So all of these guys, for the most part, are that we have an arrow above, are very similar. Let's go over here. These are called the noble gases. The noble gases are all gases. They're used to be called inert gases because they used to think they wouldn't react, but they can involve some of them in reactions now, but they're not real prone to them. So they're noble. They kind of stand off by themselves. Now, how did it get arranged like this? It got arranged because they just started noticing the properties, and they knew that when they lined them up from the smallest to the largest, so they're just lining them up, element 1, element 2, element 3, element 4. What they noticed when they did this is that there was starting to be this repeating pattern of properties. And they noticed that, hey, element number 2 and element number 10 are very, very similar. And they kept on going, and they did 11, 12, they kept lining them up, and they noticed that element number 18 was very similar to 10 and 2. So they started wrapping it around so that the elements that were similar were over top of each other. So the 2, the 10, the 18 were over top of each other. And it was all arranged according to their similar properties, chemical and physical properties. But what they noticed then was when they started studying the electronic structure, there was a reason why it got arranged this way. And we'll save that for our next learning objective. Let's finish up this grid. I hope that you finish it on your own, but if you want to check your work, you can look here at what we have. We already did the 18, 17, 18. Let's do the iron. Iron has a atomic number of, if you look at a periodic table, 26. If it's got a +3 charge, it has to have 3 less electrons. And then we would have 56 minus 26, that would be 30 neutrons. Nitrogen has 7 for its atomic number. So there's 7 protons. It has no charge. There's 7 electrons. 15 minus 7 is 8 neutrons. Oxygen is 8 for its atomic number, so that is 8 protons. It has a 2 minus charge, so it has to have 2 more electrons. And then you would take the 16 minus the 8 to get 8 neutrons. Aluminum has 13 protons because its atomic number is 13. It has a +3 charge, so it has to have fewer electrons by 3. And then we would take 27 minus 13, which is 14. So that's the completion of that grid.